All right, let's get started with our where we left off was determinants. We're doing determinants, and then we saw that we can find determinants of 2 by 2 matrices easily, and then we start looking at 3 by 3 matrices, and then higher order matrices. You can find the determinant by doing the smaller by expanding on a particular row or column. So I think that's what we were talking about last time. Yeah, I forgot what it was. So, do you guys remember what cool thing we're supposed to do? Examples. All right, let's do some cool things. Here's some examples here. So this is the last thing I pasted on, and what they want you to do is they want you to compare the determinants of the two matrices, like two at a time. And so let's take a look at the determinant of let's call these matrices. The first one let's call A. The second one let's call B. So let's say the determinant of A is it's a 2 by 2 matrix, right? So it's the product of the diagonals minus the wings. So AD minus BC. And then the determinant of B in this case is BC minus AD. So what is the difference between these two determinants? was that a hard question? Yeah, it's negatives of each other, right? They're opposites. And now let's look back at the matrix itself. And what is the difference between the two matrices? Is it transpose? The rows, there was a row switch, right? There's a row switch. So let's say at this point, that's interesting, and move on. Let's find the determinant of this next one. AB again. So the determinant of the first one is again AB minus or AD minus BC. And now the next one, this looks a little bit more complicated. Let's see. A plus KC times D minus C times B plus KD. Can we simplify this? Of course we can. AD plus KCD minus BC minus KCD. What happened? AD minus BC. Well, let's do one more and then we'll talk about row operations. So the next one is AB, again, determinant of A and B. Determinant of A equals AD minus BC. Now let's take a look at the determinant of B in this case. It's going to be A times KD minus B times KC. Looks like there's a factor of K that we can take out, right? There's a factor of K that we can take out. So it's out, and then here's what we have. So in each of these three examples that we just did, we did some sort of row operation on it from A to B. The first one was a row swap. The next one was one of those where you multiply one row by something and add it to the other row. And then the last one, you multiply a row by a scalar, right? And then so just take a look at the differences in the determinants, and it's not going to be a coincidence when we bring this up to higher dimensions. Yeah. Well, that's no good. Uh, the the LU decomposition, we're restricting ourselves to just that one. Right. Hmm. Correct. And then replace row one. Yes. You're going to change your determinants? Possibly. All right. I don't know. For the sake of practicing, you guys want to do number 23? So this is 3 by 3 matrix. So the determinant will take a little bit more work, and let's get practiced. Practiced. Let's practice finding the determinant of 3 by 3 matrix. So we have A and B. I don't see any nice zeros here, so let's just expand on, for A, let's expand on the first row. So determinant of A is going to equal to the first component of the first entry A, and then the submatrix is 2, 1, 5, 6, minus B, the submatrix for that is 3, 1, 4, 6, and then positive C, and the submatrix for that is 3, 2, 4, 5. So this is 12 minus 5 is 7, and this is 18 minus 4 is 14, and this is 15 minus 8, 7. Is that right? Hope so. Oh, I don't know. Let's find out. So let's take a look at determinant of B and see if there will be a change or there won't be a change. Um, so we can expand on any row we want. Should we expand on the second row? Let's expand on the second row. Notice that the pluses and minus here, we start with a plus in the upper left-hand corner, and then any time we make a move, we change a sign. So this starts off with a minus, right? So if we cross out the column, the first column and the first row, or sorry, the first column and the second row, I have a 2, 1, 5, 6, and then I'll switch the signs for B, and then I have 3, 1, 4, 6, and then for C, I have 3, 2, 4, 5. So that's pretty much what we have up here, except the signs are all different, right? So let's just call that negative determinant. Okay, so it still looks like the determinant of A, except it's negative. So a row swap seems like it would give us a negative of the original matrix. You think? All right, let's see if we can swap row 1 and row 3. Let's see what we get. Think? So let's swap row 1 and row 3 and create a new matrix C. So that would be 4, 5, 6, 3, 2, 1, A, B, C. How should we expand? Should we expand on the last row? What the heck? Sure. So let's expand on the last row. So this is a plus, minus is a plus. It starts off with a plus, plus A. And then what's left over after you cross out the A? You got 5, 6, 2, 1. Minus B, cross out. You got 4, 6, 3, 1. And then C, and then that would be 4, 5, 3, 2. So it's looking like it has the same positive sign, right? But look at the matrices, the little submatrices that we have. So let's compute that. We got 5 minus 12, that's negative 7, right? So any swap of any row, regardless of where it is going to generate your negative sign. So this is 4 minus 18, so it's negative, negative, and negative is a positive. And then we have 8 minus 15, and then we see that that's the opposite of determinant of A again. So any swap will generate a negative of your determinant. Okay. Let's see. There's some more interesting examples we have here. So I think we can, there's some more interesting examples that kind of leads to the second section, and that's the properties of determinants. And then by this example, or these examples that we just did, we have this, I guess this is a theorem. If you have a square matrix, then you perform one of the 3 elementary row operations, then your results will come out to be one of these. So if a multiple of one row of A is added to another row, and then you have a new matrix, then the determinants of those two matrices will be the same. Now I'm thinking maybe we should have gone back to the problems that I wanted to do. Anyways. If 2 rows are interchanged, any 2 rows, then you're going to generate a negative of your determinant. And then if you have 1 row and you're multiplying that by some constant, then your determinant is also going to be multiplied by that constant. Okay. If you just multiply a row, then it's this last one. Yeah. So those were illustrated by the problems we're doing before this page. I'm starting to think, I think I want to do the other problems that I skipped. Just a couple of them. Let's take a look at these problems. You know what these matrices? Do you know what they look like? I'm going to squeeze this in over here. Looks like we have some room on the previous page. So they look like the identity matrix, but there's something that we did to them, right? We did some elementary row operation on the matrix. These would be called elementary matrices, right? So remember that when you do an elementary row operation on the identity, you get what's called an elementary matrix. Just one, yeah. Row 2 times k plus row 3, correct. All right, let's find the determinant of this. We can expand on the first row. Actually, it's a diagonal, right? So determinant of this is equal to, let's call it A. Let's call it A1. Determinant of A1 is just 1. Determinant of A2 is what? So it should be -1. Well, should we compute it? Okay. So let's expand on the first row. So we get 0 minus 0 plus 1. So I didn't put the matrices next to the 0 because they're going to disappear anyway. So the one matrix we have here is the submatrix is 0, 1, 1, 0. And that's going to give us a 0 minus 1. So it'll be -1. Okay, so the row swap gave a -1. So yeah, this one will also be 1. If we expand on row or column, if we expand on, let's expand on this column over here, just to show you how that'll work out. I have a positive, negative, positive. So we start off with a positive k, and then the submatrix is going to be 0, 0, 1, 0. That's going to generate a 0. The next one is 0, and then the last one is 1. And then that one's going to have a submatrix of the identity. Oops, this is a plus. So this is going to be 0, this is 0, and this is going to be 1. So we have determinant is equal to 1. And then the last one should be k. Determinant of A4 is going to be expanding on the first row. We got k times 1, 0, 0, 1 plus 0. Oops, this should be a minus, but it's 0 anyways. So so this might be useful for us in finding determinants by way of doing some row reducing. Because remember, when we reduce a matrix, it's essentially multiplying by one of these elementary matrices, and then we'll see in either this section or the next section. We're going to be done with chapter 3 by today. We're going to see by the end of today that there's going to be a special property of the determinant where if you are finding the determinant of a product of a matrix, then it's like multiplying the determinants of each of those matrices. And that would be useful for the elementary operations. All right, let's go back to our newfound theorem here, which is establishing the results of the determinants of elementary matrices or matrices with elementary row operations. Okay, let's see. So let me throw out the rest of the theorems that are involved here. That will be useful for us. So this really should go in the invertible matrix theorem. Add on to the invertible matrix theorem. Where are we now? R or something, or S, something like that? A through S. So this is another one to add on. And that's to say that if your determinant's not equal to 0, then your matrix is invertible. And if that's the case, then it satisfies all those other properties that we listed last time. Some column operations. Now, we've been talking about elementary row operations. You can take the transpose and do elementary row operations and essentially do column operations that way. And so it might be good to know that the determinant of the transpose is equal to the determinant of the original matrix as well. Yes? Because there's a process called finding eigenvalues, and eigenvectors will be important for us. And we haven't talked about that. Yeah, but it itself is also a cool tool. That's up on the board right now. It also would help with like solving systems of linear equations, like in Cramers Rule. It relies on determinants of stuff. No. Or not. Just another math thing to learn. Yeah, and you'll find out when it shows up in your careers as computer scientists, data scientists, engineers. You're going to find these things coming up and say, hey, that was in linear algebra. I wish I would have paid attention. You can interrupt me. I don't care. Where are we? I got interrupted, and so I don't know where we are now. Are we on theorem 5? Theorem 5. Okay. So yeah, if turns out that the determinant of a transpose is equal to the determinant of the original matrix, which is good for us in case we wanted to do column operations instead of row operations, which leads us to the same idea. And remember that these determinants work only for square matrices. Okay. Now this is the multiplicative properties, probably the more important properties for determinants. And this one says that if you have a product AB, a product of two matrices, then the determinant of that product is equal to the determinant of each of those multiplied together. So in other words, you can say the determinant of a product is a product of their determinants. What? Oh, sure. We can do a simple example. Is there a simple example? I don't think there are any simple examples. They're just examples. Should we make one up? I don't know. I'm afraid to make one up. What? Let's do it. All right. Should we do a 2 by 2 or 3 by 3? 2 by 2? Yeah. 1, 2, 3, 4. All right. Let's throw out some numbers. I see. All right. So let's multiply these two first and then find its determinant. And then let's find its determinants and then see if we can do a comparison. So let's multiply these two. I got 5 plus 14, 19. 6 plus 16, 22. 15 plus 28, 43. And 18 plus, what is this? 50? 2? 50? Is that right? +18 plus 32? Okay. Let's find the determinant of this. Determinant of AB is equal to 19 times 50 minus 43 times 22. Suppose you can do you just punch that in the calculator. What is it? Whole thing's equal to 4. Confirm? Confirmation? Okay. So let's find the determinant of A. It's 4 minus 6 is -2, right? So we got 40 minus 42. 40 minus 42, -2. So determinant of A times determinant of B and this is not a proof. This is an example to show that this actually does work. And so that's it. Yeah. Yeah. We should. Once in a while, we'll bring up a proof. Maybe I'll just assign it for like a worksheet or something. Yeah. All right. We'll okay. I'll think about that. All right. Where are we? Okay. So why is this useful? Let's take a look at why this might be useful. Well, I mean, it's useful in a lot of different ways, but if we have some idea about the determinants of the elementary matrices, and then we have some ideas about what the products, determinants of products and matrices are, then we can do some row reducing and then find a determinant that way. So there's an interesting problem that we can try to do, and that is to use row reduction to reduce a matrix into echelon form to find its determinant. So let's take a look at number 5 for an example. Let's take a look at this 3 by 3 matrix and see if we can do some row reducing to figure out what the determinant is. I mean, we can find a determinant a regular way, right? But let's row reduce and see what we get. So for a row reduction, we're gonna do multiply the first row by 1, and then add it to the second row. We get 1, 5, -4, and this becomes a 0. And this is a positive 1, and then this is a positive 1 again. All right, now let's multiply the first row by 2 and add it to the third row to knock that 0 out again. 2 and -1. Okay, and then let's multiply the second row by -2. Add it to the third row. And what do we get? 3? -3. So we've successfully written it in row echelon form. And another way to think about this is that we could start off with this matrix. Let's see. How should I write this? Let's write it like this matrix here. 1, 5, -4, 0, 1, 1, 0, 0, -3 is actually equal to the original matrix 1, 5, -4, -1, -4, 5, -2, -8, 7. Well, I didn't say. Not done yet, yeah. So it is row equivalent, but it's obtained by doing this first step. I need to write smaller matrices here. 1, 0, 0, 1, 1, 0, 0, 0, 1. By adding the first row to the second row of the identity, right? And then also by adding 2 times the first row to the third row. So these matrices that I'm writing down are elementary row operations, right? And then I did this. I multiplied the second row by -2 added to the third row. These are all elementary row operations. Does this make sense so far? Right. So each step has its own elementary row operations. You can think about this as the original matrix A. Do some different color. You can think about this as the original matrix A, E1, E2, and E3. And then this is your new matrix B. Okay. So if you want the determinant of B or A, you want the determinant of A, right? According to that new theorem that we just got, this should be equal to the determinant of E1, determinant of E2, determinant of E3 equals determinant of B. Right? What's the determinant of E1? What's the determinant of E2? 1. Right? So if I multiplied a row by 2, then it would be 2. But I multiplied a row and then added it. So that process will give a determinant of 1. Is it hard to find a determinant of B? It's an upper triangular matrix. What's the determinant of B? So if you have an upper triangular matrix, the determinant is just the product of the diagonals. So 1 times 1 times -3, -3. So that's your determinant. Determinant of A is equal to -3. Doesn't that sound exciting? Yes. I'm very excited. Okay, so it turns out that we can use these determinants and those special theorems about the multiplicative property of determinants to find the determinants of a matrix by using the row reduction that we've been doing all along. Okay? Oh, these moves over here, the row, let's take this one. So pretend that you're doing that to your identity matrix. Where you take row 2 and then you add it to row 3. So 1, 0, 0, 0, 1, 0. Now I multiply row 2 by -2 and then add it to row 3. I get 0, -2, and 1. So that's, and if I take this matrix and literally multiply it like this, I would get this reduced form. Yeah.
What is the benefit to, say, stopping when you're just in echelon form to find the determinant of that matrix versus carrying it all the way through down to the identity, which case the determinant would change? Like, when would you look to stop in row echelon form versus taking it all the way because your determinant will be different? So what's the advantage of stopping when you have one versus, because it changes, which is weird to me.
Yeah, well, this is already in triangular matrix form. And we know the determinant of a triangular matrix is just the product of the diagonals. So if we continued on to try to reduce everything else, then we would have slightly, not much, but slightly more complicated operations to elementary row operations here, where we would multiply by some other numbers. Here, you notice that these are all ones because of the type of row operation that we did. So I won't have to worry about multiplying by constants and stuff like that. So that would be the advantage of stopping there. Well, won't be different. The determinant will still be the same, except instead of the -3 on the right-hand side, you would have a -1/3 on the left-hand side or something that you would. So the idea is still you're looking for the determinant of A. And then you would have more elementary matrices. Okay. Any questions? All right, let's see if we can do. Are there any more? You got the idea with row reducing. Let's see if we can solve one of these problems where they give you a formula for your matrix and then they're going to ask you how to find a row. What do you call it? A row operation applied onto that matrix. What the new determinant will be equal to. So here they're saying that your original matrix is A, B, C, D, E, F, G, H, I, and that's equal to 7. And so now you have a bunch of new matrices here, and they want you to find the determinant of those. So okay. So let's take a look at this. The first one. It looks like you took your identity matrix or your elementary row operation here is multiplying the third row by 3, right? So this is going to be the determinant. They use vertical lines for the determinant, so I'll do that as well. So the first one is going to give you a value of 3, and then the second one is the original matrix. So the determinant of that is 7, so this is going to be 21. Seems really easy, huh? No, it's easy. All right, 17. What happened in 17? Yeah, I don't know. Did we switch any rows? Yeah, we just scaled one row, and so. So number 17, it looks like we took the second row and added it to the first row, right? So there's a row operation here, and the row operation is taking the first row, or taking the second row, and then adding it to the first row. So that's the row operation that's being done. So what happens with that? What's your determinant of this matrix? It's just 1. So that operation where you take a row, multiply it by something, and then add it to another row is just going to give you a 1, a determinant of 1. So your determinant of your new matrix is still going to be the same. All right, how about this last one? So we just swapped 2 rows, right? So row swap will give you a -1 times 7, -7. Any questions? Seems pretty straightforward. Nah. It's going to get hard really slowly. All right, let's do one more example before we get to the volumes and areas and stuff like that. So remember that the invertible matrix theorem has a list of things that we say are all equivalent, and we just made a connection between the determinant not being equal to 0 and the matrix being invertible. And so one of the things in that list is saying that the column vectors are all linearly independent. So here they want us to use determinants to decide if the vectors are linearly independent. So what we're going to do is we're going to form a matrix out of these vectors, using these vectors as the columns, and then let's find a determinant. And if the determinant's equal to 0, then these vectors must be linearly dependent. If it's not equal to 0, then it's independent. So let's create our matrix A using these vectors as the columns. 462, -707, -3, -5, -2. And then let's just find the determinant of A. And we can expand on anything. I'd expand on a second row or second column because there's a 0 right in the middle. So let's go for the second column, and we'll assign our positives and negatives. It looks like I start here with a negative sign. So that's -7, and then cross that out, and then we get 6, -5, 2, -2. Oops, that's a -7, right? Missed that one. -7. There's a +0 times something that I'm not going to care about, and then this one's going to be a minus also. So this is a plus, and this is a minus. So that's a -7, and then cross out the row and column. You get a 4, -3, 6, -5. All right. So we have a 7 times, this looks like it's a -12 minus -10. -12 minus -10. -2? +2? -2? And then the 0's gone, and we have 7 times, and then we have a -20 minus -18. -2 again. This whole thing is equal to 0. So it turns out that determinants equal to 0. So it must follow that the matrix A is not invertible, among other things, and then the columns are not linearly. Column vectors are dependent. Okay. So another tool for finding out whether a matrix is invertible. And then you can therefore relate it. Yeah. If it's not invertible, then yeah, the columns are going to be dependent. If it is invertible, then it's independent for sure. Yeah, yeah. That's a nice thing about that theorem. The inverse matrix theorem categorizes these square matrices into one of two categories. It's either invertible or not invertible. And if it's invertible, then it satisfies everything in there. And if it's not invertible, then it satisfies nothing in there. It's all or nothing. That's what's cool about that theorem. All right. Last section in this chapter is some sort of applications to the determinant, and the first one being Cramers Rule. And Cramers Rule is a simple rule that says that if you have an invertible matrix, then you can find a unique solution to your equation ax plus b. But that's, that part of the theorem is given in the invertible matrix theorem. But here, Cramers Rule actually allows you to find the solutions for these things. So this might seem like a cumbersome way to find a solution, but if you're in the differential equations class, you'll see maybe tomorrow or Tuesday that this Cramers Rule will be important for us. So let's do a simple 2x2 system of linear equations. I don't know. Let's say x plus y is equal to 4, and then x minus y is equal to 2. Let's go really simple here. Hopefully these two lines intersect, right? They have different slopes, so they should intersect. And so this is how you would think about using Cramers Rule. First of all, if you adjust your way of thinking and say this is a matrix 1, 1, 1, negative 1 multiplied by x, y, and this is equal to b, then you can view this equation, the system, as a matrix equation with the appropriate vectors, the x that you're looking for, and then the b that you're given. And so now you have the matrix A. So what they're saying is that well, you could solve for this in a bunch of different easy ways, but we're going to solve for this using Cramers Rule. And Cramers Rule says that the ith x coordinate that you're looking for is going to be the determinant of, and what this symbol says is that it's the original matrix, but you're going to replace the ith column by the vector b. So in this particular example, since it's a 2x2 matrix, we have determinant of 1 parentheses b that we need to find. So what is the matrix 1 or A1 parentheses b? That's going to be this matrix. Now don't write this yet because I'm going to erase something. Oops, that should be a 1. But instead of, what should I do? Instead of using the original matrix, you're going to replace your first column by this vector b, 4 and 2. Okay, so it's your matrix A, and then you're going to replace one of the columns with the vector b. Yeah. So I is going to be 1 through n. So in this case, I is going to be 1, I is going to be 2, and those are the only two that we have. And so we're going to figure out what A2 of B is going to equal to. So this is A1 of B, and A2 of B is going to be the same matrix, except instead of the second column, why is it moving? Instead of the second column, we're going to replace the second column with the B matrix. So that's 4, 2. Okay. So we'll find the determinants of these. So the determinant of A1, B is going to be -4 minus 2, -6. Determinant of A2, B is going to be +2 minus 4, -2. And we also need the determinant of A. And so A is this matrix over here. What's that? Yeah, -2. Okay. So your solutions, your x1, in this case, your x is equal to the quotient of determinant A1b divided by the determinant of A. So that's -6 divided by -2. That's +3. And then y, or x2, is going to be the determinant of A2b over the determinant of A, which is going to be -2 over -2, 1. And so you plug that in to make sure that it actually does satisfy your system, and it looks like it does. So that's how we do Cramers Rule. So again, it seems long-winded, but there are more significant applications to Cramers Rule than trying to solve for systems, because systems, we can solve for them by just row reducing or whatever it is we've been doing. Okay. This has a more powerful use when you're dealing with, like the Wronskian or something. What? What's a Wronskian? All right. Another formula for the inverse is in the book. I don't really care about this because it has an adjoint, the classical adjoint. Why don't I just put this in our notes and just say, read about it? It's in our notes. You don't have to copy it down. The more interesting application would be the last one that they have in this section, which is about areas and volume. So if you have a 2 by 2 matrix, the area of the parallelogram determined by the columns of A is the determinant. So this is an actual now geometric application to matrices. Absolute value, because it might be negative and you just want to compensate for negatives. And if you have a 3 by 3 matrix, then you're talking about vectors in R3, and that's the space, a three-dimensional object spanned by 3 vectors, and that's called the parallelepiped. So it's like a parallelogram, except it's in 3D, and then all those sides are all going to be parallel to each other. So let's take a look at a simple 2 by 2 case. I don't know. Let's say V1 is equal to, let's find a 2 vector. All I can think of is 1, 2, 3, 4. No, I was thinking even simpler. It's just 1, 0. That seems lame. All right, let's shake it up a bit. Let's let V2 equal to 3, 2. And that's shaking up right there. So if we take a look at this geometrically, the 1, 0 vector is just this thing here. And the 3, 2, 1, 2, 3, and then 1, 2, 3 vectors right here. So if we take a look at this parallelogram, this should be easy to do. We can find this without using vectors, right? Find the volume or area of this. How do you find the area of this? It's base times height. Yeah, it's parallelogram, base times height. So the base is 1, the height is 2, so the answer should be 2, right? All right, well, let's see that this is actually going to be the area by forming your 2 by 2 matrix 1, 3, 0, 2. So the determinant of A is going to be 2 minus 0, which is 2. And that just matches the area. Okay. Now, for a 3 by 3 example, if you've taken Calc 3, that was one of the cross product applications. Is aside from figuring out, you know, the determinant of a 3 by 3 matrix with the IJK, you can figure out the determinant of 3 by 3 matrix of 3 vectors, and you actually will find the volume of the parallelogram. So one more theorem in this section. If you have a linear transformation from a 2 by 2 matrix and then to something else, then it's going to distort your image that you have. So let's say we start off with a square parallelogram, and then we run it through a linear transformation, and it becomes skewed or whatever happens. Then that area, the new area, is going to get compensated by the determinant of your matrix. So this turns out to be, for the linear case, it turns out to be, I don't know if you guys are familiar with a Jacobian, but when you transfer, it's like a U substitution for multiple variable calculus, for multiple integrals. And so if you move from one object, and then it's hard to integrate this object, so you move it to another object that might be easier to integrate, then you need to compensate for how the area changes. And so, yeah, the change of coordinate system, and the change of coordinate system will rely on the determinant of your transformation. Yeah. So I don't know if I pulled out any problems in this section. I didn't pull out any problems in this section, so you guys just have to try to do it on your homework. I have 2 minutes. That's about how long it's going to take me to pull out the. If I do it slow enough, we'll run out of time. Yeah. What's going on? There he goes. Let's look at this simple linear transformation. Simple. Oh, we're even going in R3. So let's say we have a linear transformation here determined by this matrix where A, B, and C are positive numbers. And then S is your sphere, x squared plus y squared plus z squared. Show that T of S is bounded by the ellipsoid. So when we transform your sphere through this transformation, it's going to elongate your x, elongate your y, and elongate your z by A, B, and C, and then it'll create a sphere. Yeah. Oh, we're out of time. So good luck with this. See you guys on